Hello world, I'm Carrie-Anne and welcome to Crash Courses.
Release เดินก็หกนะ Sorry guys. Alright, so let's continue to this. Let's continue. My apology.
Hello world, I'm Carrie-Anne and welcome to Crash Courses Science. Over the course of this series, we're going to go from bits, bytes, transistors and logic gates, all the way to operating systems, virtual reality and robots. We're going to cover a lot, but just to clear things up, we are not going to teach programs. Instead, we're going to explore a range of topics, the disciplines and the technique. Computers are the lifeblood of today's world. If they were to suddenly turn off all at once, the power grid would shut down, planes would fall, water treatment plants would stop, markets would freeze, trucks wouldn't know where to deliver, and employees wouldn't get paid. Even many non-computer objects, like DFCDA shirts and the chair I'm sitting on, are made in factories run by computers. Computing really has transformed nearly every aspect of our lives. And this isn't the first time we've seen this sort of technology-driven global change. Advances in manufacturing during the Industrial Revolution brought new scale to civilization, agriculture, industry and life. Mechanization makes superior harvest, more food, mass-produced goods, cheaper and faster travel and communication, and usually a better quality. And computing technology is doing the same right now. From automated farming and medical equipment, global telecommunications and educational opportunities, and new frontiers like virtual reality, self-driving cars. We are living in a time likely to remember as being electronic. And with billions of transistors in just your smartphone, computers can seem complicated. But really, they're just simple machines that perform complex actions through many layers of action. So in this series, we're going to break down those and build up from ones and zeros, logic units, CPU, operating systems, the entire internet, and beyond. And don't worry, in the same way someone buying t-shirts on a web page doesn't need to know how that web page is programmed, or the web designer doesn't need to know all the packages or router engines don't need to know about this logic. This series will build on previous episodes, but not be dependent. By the end of this series, I hope that you can better contextualize computing both in your own life and how humanity's arguably greatest invention is just in its infancy, with its biggest impact yet. But before we get into all that, we should start at its origins. Because although electronics are relatively new, the need for computation is not. The earliest recognized device for computing was the abacus, invented in Mesopotamia around 2500 BCE. It's essentially a hand-operated calculator that helps add and subtract many numbers. It also stores the state of the computation, much like your hard drive does. The abacus was created because the scale of society is greater than what a single person can manipulate in their mind. There might be thousands of people, or tens of thousands of people. There are many variants of the abacus. Let's look at a really basic one, with each row representing the power of 10. So each bead on the bottom row represents a single unit. The next row, they represent 10, row above, 100, so on. Let's say we have 3 heads of cattle represented by 3 beads on the bottom row right side. If we were to buy 4 more cattle, we would just slide 4 more beads for a total of 7. But if we were to add 5 more after the first 3, we would run out of beads. So we would slide everything back to the Slide one bead on the second row to the right, representing 10, and then add the final two beads on the bottom row for a total of 12. This is particularly useful with large numbers. So if we were to add 1,251, we would just add 1 to the bottom row, 5 to the second row, 2 to the third row, and 1 to the fourth row. We don't have to add in, and the abacus stores the total for us. Over the next 4,000 years, humans developed all sorts of clever computing devices, like the asteroid, which enabled ships to calculate their latitude, or the slide rule, assisting with multiplication and division. And there are literally hundreds of clocks created that could be used to calculate sunrise tides, positions of celestial bodies, and even just the time. Each one of these devices is something that was laborious to calculate, faster, easier, and often more accurate. It lowered the barrier to entry, and at the same time amplified our mental ability. Take note. This is a theme we're going to touch on a lot in this series. As early computer pioneer Charles Babbage said, at each increased knowledge, as well as on the contrivance of every new tool, human labour was abridged. However, none of these devices were computers. The early
Human labor. What does that mean, man? Human labor. Rich. Like I know what a bridge is, but like a bridge. Have been shortened. So hope each piece knowledge as well on the contrivance of every new truth. So the more knowledge and you build new tools and you reduce human labor. Yes. Makes sense. Makes sense.
Human labour becomes abridged. However, none of these devices were computers. The earliest documented use of the word computer is from 1613 in a book by Richard Braithwaite. And it wasn't a machine at all, it was a job title. Braithwaite said, I have read the truest computer times and the best arithmetic that ever breathed. He reduced it by days into short numbers. In those days, a computer was a person who did calculations, sometimes with the help of machines, but not. This job title persisted until the late 1800s, when the meaning of computers started to shift to refer to devices. And notable among these devices was the step reckoner built by German polymath Leibniz in 1694. Leibniz said it is beneath the dignity of excellent men to waste their time in calculation when any person could do the work accurately with the aid of a machine. It worked kind of like the odometer in a car, which is really just a machine for adding up.
Teachers bombs them. Just bombs them.
The aid of a machine. It worked kind of like the odometer in a car, which is really just a machine for adding up the number of miles driven. The device had a series of gears that turned. Each gear had 10 teeth, represent the digits from 0 to 9. Whenever a gear applied plus 9, it rotated back to 0 and advanced the adjacent gear by 1. Kind of like when hitting 10 on that basic abacus. This worked in reverse when doing some 2. With some clever mechanical tricks, the step reckoner was also able to multiply numbers. Multiplications and divisions are really just many additions and subtractions. For example, if we want to divide 17 by 5, we just subtract 5, then 5, and 5 again, and then we can't subtract any more 5. So we know 5 goes into 7 3 times, with 2 left over. The step reckoner was able to do it automated and was the first machine that could do all 4 of these operations. And this design was so successful, it was used for the next 3 centuries of calculating. Unfortunately, even with mechanical calculators,
this is like
many steps of computation
ancient calculators.
Take hours or days to get a single result. Also, these handcrafted machines were expensive, not accessible to most nations. Before the 20th century, most people experienced computing pre-computed tables assembled by those amazing humans we talked about. So if you needed to know the square root of 8,675,309, instead of spending all day hand cranking step reckoner, you could look it up in a huge book of square root tables in a minute or so. Speed and accuracy is important on the battlefield. And so militaries were among the first to apply complex problems, particularly difficult.
Like every new technology. If there's a new technology that come out on anything, the first people to like adopt it is probably the military. And this is applied to anything. The computers, yeah, like every single weapons nowadays, like rockets and stuff, all have really like trackers and stuff like that. I don't know. Like anything that come out, anything new technology that comes out. Yeah, the military just adopted everything.
Problem is accurately firing artillery shells, which by the 1800s travel well over a kilometre, or a bit more than half a mile. Add to this varying wind conditions, temperature, and atmospheric pressure, and even hitting something as large as a ship was. Range tables were created that allowed gunners to look up environmental conditions and the distance they want to fire, and the table would tell them the angle to cannon. These range tables worked so well, they were used well into World War II. The problem was, if you changed the design of the cannon or shell, a whole new table had to be used, which was massively time-consuming and inevitably led to errors. Charles Babbage acknowledged them in 1822 in a paper to the Royal Astronomical Society entitled Note on the Application of Machinery to the Computation of Astronomical Tables. Let's go to the full. Charles Babbage proposed a new mechanical device with a different engine, a much more complex machine that approximate polynomials. Polynomials describe the relationship between several variables, like range and air pressure, or amount of heat and happiness. Polynomials could also be used to make logarithmic and trigonometric functions, which are a real hassle to calculate by hand. Babbage started construction in 1820, and over the next 2 decades tried to fabricate and assemble 25,000 components, collectively weighing around 15 tons. Unfortunately, the project was ultimately abandoned. But in 1991, historians finished constructing a different engine based on Babbage's writings, and it worked. But more importantly, during construction of the difference engine, Babbage imagined an even more complex machine, the analytical engine. Unlike the difference engine that reckoned on all other computational devices before it, the analytical engine is a general purpose. It could be used for many things, not just one computation. It could be given data and run operations, sequence, memory, and even a printer. Like the difference engine, it was ahead of its time, was never fully constructed. However, the idea of an automatic computer, one that could guide itself through a series of operations automatically, was a huge deal. Would foreshadow computer programs. English mathematician Ada Lovelace wrote hypothetical programs for the analytical engine, saying a new, vast, and powerful language for the future use of analysis. For her work, Ada is often considered the world's first programmer. The analytical engine would go on to inspire arguably the first generation of scientists who incorporated many of Babbage's ideas in them. This is why Babbage is often considered the father of computing. Thanks, Sport Bubble. So by the end of the 19th century, computing devices were used for computing. Thanks, Sport Bubble. So by the end of the 19th century, this is why Babbage generation of scientists who incorporated many of Babbage's through a series of operations automatically was a huge deal. Would foreshadow computer programs. English mathematician Ada Lovelace wrote hypothetical programs for the analytical engine, saying a new, vast, and powerful language for the future use of analysis. For her work, Ada is often considered the world's first programmer. The analytical engine go on to inspire arguably the first generation of scientists who incorporated many of Babbage's ideas. This is why Babbage is often considered the father of computing. Thanks, Sport Bubble. So by the end of the 19th century, computing devices were used for special purpose tasks in the sciences and engineering, rarely seen in business, government, or life. However, the US government faced a serious problem in the 1819 census that demanded the kind of efficiency that only computers provide. The US Constitution requires that a census be conducted every 10 years for the purposes of distributing federal funds, representation and good stuff like that. And by 1880, the US population was booming, mostly due to immigration. That census 7 years to manually compile. By the time it was completed, it was already out of date. It was predicted that the 1890s would take 13 years to complete. That's a little problematic when it's required every decade. The Census Bureau turned to Herman Hollerith, built a tabulating machine. His machine was electromechanical. It used traditional mechanical systems for keeping count, Like Leibniz is step record, but coupled them with electrically powered components. Polaris machine used punch cards, which were paper cards with a grid of locations punched out to represent data. For example, there was a series of holes for marital status. If you were married, punch out the married spot. Then when the card was inserted into Polaris machine, this whole metal would come down over the card. The spot was punched out, pin would pass through the hole in the paper into a little vial of mercury, which completed the circuit. This now completed circuit powered an electric motor, which turned a gear to add one. In this case, the married tone. Polaris machine was roughly 10 times faster than manual tabulation. And the census was completed in just 2.5 years, saving the census of millions of dollars. Businesses began recognizing the value of it and saw its potential to boost profits by improving labor, data-intensive tasks like accounting, insurance appraisals, and inventory management. To meet this demand, Hollerith founded the tabulating machine, which later merged with other machine makers in 1994 to become the International Business Machines Corporation, or IBM, which you've probably heard of. These electromechanical business machines were a huge success, transforming commerce and government. By the mid-1900s, the explosion in world population and the rise of globalized trade demanded even faster and more flexible tools for processing data, setting the stage for computers, which we'll talk about next week. Crash Course Computer Science is produced in association with PBS Digital. At their channel, you can check out a playlist of shows like PBS Idea Channel, Physics Girl, Go-KTB. This episode was filmed at the Chad and Stacey Emergold Studio in Indianapolis, Indiana. It was made with the help of all these nice people and our wonderful
guys. Always watch until the end of the video, just to like YouTube think that, oh, you finished. They're going to recommend us all of this, which just like it's smart, right? You know, we'll get all of this recommended. Gonna get all of this recommended to you. You know, it's like that. So you can watch it all day.
Với bộ áo Việt Nam Thi chất vải.
Our last episode brought us to the start of the 20th century, where early special purpose
Right, give me a moment.
devices.
Give me a moment.
Tabulating machines were a huge boon to government business, aiding and sometimes replacing rote manual tasks. But the scale of human systems continued to increase at an unprecedented rate. The first half of the 20th century saw the world's population almost double. World War I mobilized 70 million people, and World War II involved more than 100 million. Global trade and transit networks became interconnected like never before, and the sophistication of our engineering and scientific endeavors.
I feel like wars, like World War II and World War I, it's extremely devastating. But like the technology go from here to like whoop, after just the two wars. Feel like, I don't know, war is really like whenever there's a war, like the development like you go to the moon. So is war really is so if you're looking at that perspective, would you think that war is bad because people associate war to being really a bad thing? But yeah, it is really devastating, like, to humanity. But the development, the technologies, everything else, like because of World War II, if you're looking, if you're like looking at on the other side of the problem, like not the bad side, good side, you have so many more new technology. Basically, the foundation for a lot of the I'm not a native English speakers, but what is it? Station new industry, especially visual intelligence, Alan Turing machine, and the V2 bombs, which is basically the foundation, which is basically the first ever like intercontinental missile. Like can fly from like Germany to like the US. And then because of that is like the mothers of space rocket. Yeah. I think it is. And then there's a whole bunch of things, radars and then like computers, like it just sparked.
Reach new heights.
Well, yeah. Let's just skip that, and we will go back to studying. Okay.
Started to seriously consider visiting other planets. And it was this explosion of complexity, bureaucracy, and ultimately data that drove an increasing need for automation and computation. Soon those cabinet-sized electromechanical computers grew into room-sized behemoths that were expensive to maintain and prone to error. And it was these machines that would set the stage for future innovation. One of the largest electromechanicals built was the Harvard Mark I. Completed in 1944 by IBM, the Allies during World War II. It contained 765,000 components, 3 million connections, 500 miles of wire. To keep its internal mechanics synchronized, it used a 50-foot shaft running right through the machine, driven by a 5-horsepower motor. One of the earliest uses of this technology was running simulations for the Manhattan Project. The brains of these huge electromechanical beasts were relays, electronically controlled mechanical switches. In a relay, there is a control wire that determines whether a circuit...
What is the Manhattan Project? Oh, it's a nuclear project. Ah. I see. Oh, yes. I remember. I was like, oh,
The control wire connects to a coil of wire inside the relay. When current flows through the coil, an electromagnetic field is created. In turn, tracks a metal arm inside the relay, snapping it shut and completing the circuit. You can think of a relay like a water faucet. The control wire is like the faucet handle. Open the faucet and the water flows through the pipe. Close the faucet and the flow of water stops. Relays are doing the same thing, just with electrons instead of water. The controlled circuit can then connect to other circuits or to something like a motor, which might increment a count on gear, like in Hollerith's tabulating machine we talked about last episode. Unfortunately, the mechanical arm inside of a relay has mass, and therefore can't move instantly open and closed state. A good relay in the 1940s might be able to flick back and forth 50 times in a second. That might seem fast, but it's not fast enough to be useful at solving large, complex problems. The Harvard Mark I could do 3 additions or subtractions per second. Multiplications 6 seconds, and divisions 15, and more complex operations like a trigonometric function take over a minute. In addition to slow switching speed, another limitation is wear and tear. Anything mechanical that moves wear over time. Some things break entirely and other things start getting slow and just unreliable. And as the number of relays increases, the probability of a failure increases too. The Harvard Mark I had roughly 3,500 relays. Even if you assume a relay has an operational life of years, this would mean you would have to replace, on average, 140 relay every day. That's a big problem when you're in the middle of running some important multi-day calculations. And that's not all engineers had to contend. These huge dark and war machines also attracted insects. In September 1947, operators on the Harvard Mark II pulled a dead moth from a malfunction relay. Grace Hopper, who we'll talk more about in a later episode. From then on, when anything went wrong with a computer, we said it had bugs in it. And that's where we get the term computer bug. It was
computer bugs is actually coming from like a bug dying. It's actually genius. And now I was wondering why is bugs? Why is it called bugs? It can cause errors. Why is it called bugs? Now I see. There's a literal bugs dying in the computer. Okay.
But a faster, more reliable alternative to electromechanical relays was needed. Computing was going to advance further. Unfortunately, that alternative already existed. In 1904, English physicist John Ambrose Fleming developed a new electrical component called a thermionic valve, which housed two electrodes inside an air glass bulb. This was the first vacuum tube. One of the electrodes heated, which would cause it to emit electrons, a process called thermionic emission. The other electrode could then attract these electrons to create the flow of our electric faucet, but only if it was positively charged. If it had a negative or neutral charge, the electrons would no longer be attracted across the vacuum, so no current would flow. Any electronic component that permits the one-way flow of current is called a diode. But what was really needed was a switch to help turn this flow on and off. Luckily, shortly after in 1906, American inventor Lee Forrest added a third control electrode that sits between the two electrodes in Fleming's design. By applying a positive charge to the control electrode, it would permit the flow of electrons before. But if the control electrode was given a negative charge, it would prevent the flow of electrons. So by manipulating the control wire, one could open or close the circuit. Pretty much the same thing as a relay, but importantly, vacuum tubes had no moving parts. This meant there was less wear, and they could switch thousands of times per second. These triode vacuum tubes become the basis of radio, long-distance telephone, and many other electronic devices for nearly half a century. I should note here, vacuum tubes weren't perfect. They're kind of fragile and burn out like light bulbs, but they were a big improvement over mechanical relays. Also, initially, vacuum tubes were expensive. A radio set often used just one, but a computer might require hundreds or thousands of electrical switches. But by the 1940s, their cost and reliability had improved to the point where they became feasible for computers. At least by people with deep pockets, like government. This marked the shift from electromechanical computing to electronic computing. Let's go to the thought bubble. First large-scale use of vacuum computing was the Colossus Mark I, designed by engineer Tommy Flowers and completed in December of 1943. The Colossus was installed at Bletchley Park in the UK and helped decrypt Nazi communications. This may sound familiar because 2 years prior, Alan Turing, often called the father of science, had created an electromechanical device also at Bletchley Park called the bomb. It was an electromechanical machine designed to break Nazi Enigma code. But the bomb wasn't technically a computer. And we'll get to Alan Turing's computer later. Anyway, the first version of Colossus contained 1,600 vacuums. And in total 10 colossi were built to help with code breaking. Colossus is regarded as the first programmable electronic computer. Programming was done by plugging hundreds of wires into plug boards, sort of like old telephone switchboards, in order to set up the computer to perform the right operation. So while programmable, it still had to be configured to perform any specific computation. Enter the electronic numerical integrator and calculator, or ENIAC, completed a few years later in 1996 at the University of Pennsylvania. Designed by John Muttley and J. Prescott Eckert, this was the world's first truly general-purpose programmable electronic computer. ENIAC could perform 5,000 10-digit addition transactions per second, many times faster than any machine before it. It was operational for 10 years, and it's estimated to have done more arithmetic than the entire human race up to that point. But with that many vacuum tubes, failures were common. ENIAC was generally only operational for about half a day at a time before breaking down. Thanks, Thought Bubble. By the 1950s, even vacuum tube-based computing was reaching its limit. The US Air Force's ANFS-7 computer, which was completed in 1955, was part of the Stage Air Defense Computer System, which we'll talk about more.
Another military application. Every new technology that came out, the military would use it. So, what if you can in the military? Would you be like the first person to you would be the first person to touch any technology, new technology? You have
or in a later episode.
Let's keep that in mind.
Reduce cost and size, as well as improve reliability and speed. A radical new electronic switch was needed. In 1947, Bell Laboratory scientist John Barden, Walter Brittain, and William Shockley invented the transistor, and with it a whole new era of computing born. The physics behind transistors is pretty complex, relying on quantum mechanics. So we're going to stick to the basics. A transistor is just like a relay or vacuum. It's a switch that can be opened or closed by applying an electrical power via a control wire. Typically, transistors have two electrodes separated by a material that sometimes can conduct electricity and other times resist it. A semiconductor. In this case, the control wire attaches to a gate electrode. By changing the electrical charge of the gate, the conductivity of the semiconducting material can be manipulated, allowing current to flow or be stopped. Like the water faucet analogy we discussed earlier. Even the very first transistor at Bell Labs showed tremendous promise. It could switch between on and off states 10,000 times per second. Further, unlike vacuum tubes made of glass and with carefully suspended fragile components, transistors were solid material, known as a solid-state component. Almost immediately, transistors were made smaller than the smallest possible relays or vacuums. This led to dramatically smaller and cheaper computers, like the IBM 608, released in 1907, the first fully transistor-powered commercially available computer.
That's look like a clean. That's look like a fridge now. It is probably the nicest back then. Probably the smallest one too. Look like a fridge nowadays. Or like a old kitchen. You have the fridge. You have the fridge, and on the top.
In 1957, the first fully transistor-powered commercially available computer. It contained 3,000 transistors and could perform 4,500 additions, or roughly 80 multiplications every second. IBM soon transitioned all of its computers to transistors, bringing transistor-based computing into offices and eventually. Today, computers use transistors that are smaller than 50 nanometers size. For reference, a sheet of paper is roughly 100,000 nanometers thick. And they're not only incredibly small, they're super fast. They can switch states millions of times per second and can run for decades. A lot of this transistor and semiconductor development in the Santa Clara Valley between San Francisco and San Jose, California. Since the most common material used to create semiconductor silicon, this region soon became known as Silicon Valley. Even William Shockley knew, founding Shockley Semiconductor, whose employees later founded Fairchild Semiconductors, whose employees later founded Intel, the world's largest chip maker today. Okay, so we've gone from relays to vacuum transistors. We can turn electricity on and off really fast. But how do we get from transistors to actually computing something? Especially if we don't have motors and gears. That's what we're going to cover over the next 2 episodes. Thanks for watching. See you next week. Crash Course Computer Science is produced in association with PBS Digital Studios. At their channel, you can check out playlists of shows like Braincraft, Comanidi, and PBS Infinite Series. This episode was filmed at the Chad and Stacey Emigalt Studio, Indianapolis, Indiana. It was made with the help of all these nice people and our wonderful graphics team, Thought Cafe. Thanks for the random access memories. I'll see you next time.
Just watch all of them. Not the ads, so. Not the ads. Oh, wait. Yeah, let's watch the ads. Oh.
Top Talent has definitely elevated my game. It's the best of the best.
I get to work with sorts of different clients.
Through Top Talent, I have a huge variety of projects that I can work on.
100 job postings. You get to filter through them and see what looks interesting.
I get to choose who I want to work with and when I want to work with them.
It's been an amazing experience of growth.
Now we skip. Alright. Oh, Boolean logic.
Welcome to Crash Course Science. Today we start our journey up the ladder of abstraction, where we leave behind the simplicity of being able to see every gear, but gain the ability to assemble increasingly complex systems. last episode, we talked about how computers evolved from electromechanical devices that often had decimal representation.
Guys, I have a good yoke. Good yoke. What? Wait. Okay. If you have a skinny girlfriend, what do you call them? A boolean. Okay, let's watch the
Of numbers, like those represented by teeth and gear, to electronic computers with transistors that can turn the flow of electricity on or off. Unfortunately, even with just two states of electricity, we can represent important information. We call this representation binary, which literally means of two states. In the same way a bicycle has two wheels or a biped has two legs. You might think two states isn't a lot to work with, and you'd be right. But it's exactly what you need for representing the values true and false. In computers, an on state when electricity is flowing represents true. The off state, no electricity flowing represents false. We can also write binary as ones and zeros, trues and falses. They're just different expressions of the same signal. But we'll talk about that in the next episode. Now it is actually possible to use transistors for more than just turning electrical current on and off, and to allow for different levels of current. Some early electronic computers were ternary, that's 3 states, and even quinary uses 5 states. The problem is, the more intermediate states there are, the harder it is to keep them all separate. If your smartphone battery starts running low, or there's electrical noise because someone's running a microwave nearby, the signals can get mixed up. And this problem only gets worse with changing states millions of times per second. So placing two signals as far apart as possible, using just on and off, gives us the most distinct signal to minimize these issues. Another reason to use binary is that an entire branch of mathematics already existed that dealt exclusively with true and false values, and it had figured out all the necessary operations for manipulating them. It's called Boolean algebra. George Boole, from which Boolean algebra later got its name, was a self-taught English mathematician in the 1800s. He was interested in representing logical statements that went under, over, and beyond Aristotle's approach to logic, which was unsurprisingly grounded in philosophy. Boole's approach allowed truth systematically and formally proven through logic equations, which he introduced in his first book, Mathematical Analysis of Logic, in 1847. In regular algebra, type you probably learned in high school, the values of variables, numbers, and operations on those are things like addition and multiplication. But in Boolean algebra, the values of variables are true and false, and the operations are logical. There are three fundamental operations in Boolean algebra: a not, an and an or operator. And these operations turn out to be really useful. So we're going to look at them individually. A not takes a single Boolean value, either true or false, and negates it. It flips true to false to true. We can write out a little logic table that shows the original value under input, and the outcome after applying the operation under output. Now here's the cool part. We can easily build Boolean logic out of transistors. As we discussed last episode, transistors are really just electric-controlled switches. They have 3 wires, 2 electrodes, and 1 control wire. When you apply electricity to the control wire, lets current flow through from one electrode through the transistor to the other electrode. This is a lot like a spigot on a plate. Open the tap, water flows. Close the tap, water shuts off. You can think of the control wire as an input, and the wire coming from the bottom electrode, the output. So with a single transistor, we have one input and one output. If we turn the input on, the output is also on, because the current can flow through it. If we turn the input off, the output is also off, and the current no longer passes. Or in Boolean terms, when the input is true, the output is true. And when the input is false, the output is also false. Which again, we can show on a logic table. This isn't a very exciting circuit, though. It's not doing anything. The input and output is the same, but we can modify the circuit just a little bit and not. Instead of having the output wire at the end of the transistor, we can move it before. If we turn the input on, the transistor allows current through it to the ground, and the output wire won't receive that current, so it will be off. In our water metaphor, grounding, like if all the water in your house was flowing out of a huge hose, there wasn't any water temperature shower. So in this case, input is on, output is off. When we turn off the transistor, though, current is prevented from flowing down into the ground. So instead, current flows through the output wire. So the input will be off and the output will be on. And this matches our logic table for NOT. So congrats, we just built a circuit with NOT. We call them NOT gates, and we call them gates because they're controlling the path of output. The AND Boolean operation takes two inputs, but still has a single output. In this case, the output is only true if both inputs are true. Think about it like telling the truth. You're only being completely honest. You don't lie little. For example, let's take the
It's
statement.
like the plus plus, minus minus, equal plus, and plus minus, minus plus. False. Nice.
My name is Carrie Ann, and I'm wearing a dress. Both of those facts are true, so the whole statement is true. But if I said my name is Carrie Ann and I'm wearing pants, that would be false, because I'm not wearing pants. Or trousers, if you're in England. The Carrie Ann part is true, but a true and a false is still false. So if I were to reverse that statement, it would still obviously be false. And if I were to tell you two lies, that is also false. And again, we can write all of these.
Not minus minus, not equal to. Or suppose. Okay, so it's like plus plus true. Plus minus false. Minus plus false. Then minus minus is
combinations out in a table. To build an AND gate, we need two transistors connected together so we have our two inputs and one output. If we turn on just transistor A, current won't flow because current is stopped by transistor B. Alternatively, if transistor B is on, transistor A is off. Same thing. Current can't get through. Only if transistor A and transistor B are on, does the output wire have it. The last Boolean operator is OR, where only one input has true for the output. For example, my name is Margaret Hamilton, or I'm wearing a dress. This is a true statement, because although I'm not Margaret Hamilton, unfortunately, I am wearing a dress. So the overall statement is true, and OR statement is also true if both facts are true. The only time an OR statement is false is if both inputs are false. Building an OR gate from transistors needs a few extra wires. Instead of having two transistors in series, one after the other, we have them in parallel. We run wires from the current source of both transistors. We use this little arc to note that the wires jump over one another.
wait, what is and should be like continuous.
Logic table from NOT. Current is prevented from flowing down into the ground.
So not. Oh, I see. Here, round.
So instead, current flows huge hose. There wasn't any water pressure shower. So in this case, input is
On.
output is off. When we turn off the transistor, though, current is prevented from flowing down into the ground.
Not.
So instead, current flows through the output wire. So the input will be off and the output will be on. And this matches our logic table for NOT. So congrats, we just D for the AND and a spaceship law of abstraction. The standard is also on. Also, if both transistors are on, the output is still on. Okay, now we've got NOT and OR gate. And we can leave behind their transistors and move up a layer of abstraction. The standard engineers use gates are a triangle with a dot for it, a D for the AND, and a spaceship law. Those aren't the official names, that's how I like them. Representing them and thinking about them this way allows us to build even bigger components while keeping the overall complexity relatively the same. Just remember that all of the transistors and wires is still there. For example, another useful Boolean operation in computation is called an exclusive OR, or XOR. XOR is like a regular OR, but with one difference. If both inputs are true, the XOR is false. The only time an XOR is true is when one input is true and the other input is false. It's like when you go out to dinner and your meal comes with a side salad or a soup. Sadly, you can't have both. And building this from transistors is pretty confusing, but we can show how an XOR is created. Three basic building gates. We know we have two inputs, A and B, and one out. Let's start with an OR gate. Since the logic table is almost identical to an OR. There's only one problem. When A and B are true, the logic is different, and we need to output false. To do this, we need to add some additional gates. If we add an AND gate and it's true, the output will be true. This isn't what we want. If we add a not immediately after, this will flip it to false. Okay, now if we add the final AND and send it that value along with the our original OR gate, the AND will take in false and true. And since AND means both values true, its output is false. That's the first row of our logic table. If we work through the remaining input combinations, we can see this Boolean logic does implement an exclusive OR. And XOR turns out to be a very useful component. And we'll get to it in another episode. So useful, in fact, engineers gave it symbol too. An OR gate with a smile. But most importantly, we can now put XOR into our metaphorical tool and not have to worry about the individual logic gates make it up, or the transistors that make up those gates, or how electrons are flowing through a semiconductor, moving up another layer of abstraction. When computer engineers are designing processes, they rarely work at this level and instead work with much larger blocks, like logic gates, and even larger components made up of logic gates, which we'll discuss in future episodes. And even if you are a computer programmer, it's not often that you think about how the logic that you are programming is actually implemented in the physical world by these teeny tiny components. We've also moved from thinking about raw electrical signals to our first representation of data, true and false. And we've even gotten a little computation with just the logic gates in this episode. We could build a machine that evaluates complex statements, like if name is John Green and after 5, or is weekend and near pizza, then John will want that equals true. And with that, I'm starving. I'll see you next week. Crash Course Computer Science is produced in association with PBS Digital Shows. At their channel, you can check out a playlist of shows like Growth Science, ACS Reactions, and The Art of Science. This episode was filmed at the Travis Stacey Emigott Studio, Indianapolis, Indiana. It was made with the help of all these nice people and a wonderful graphics Thought Cafe. Thanks for watching.
I would love some pizza too, but not right now. I'm having worse runny nose. Oh God.
What? Still searching YouTube for math help? Are the videos from 2006 really helping? Aren't you tired of finding videos that aren't getting you anywhere in math class? Try something new now. Join thousands of other students who do a lot better in math with StudyPug, Math's best friend. Here's how StudyPug Select your course of interest from elementary to high school math, stats, calculus, and college algebra. Click on the course. There are a wide selection of topics covered by your teacher. If you're not sure about a topic, hover over it to see the examples. You can also use our awesome real-time search. Now, let's select the topic. You're now in the page where the magic happens. On the top, you can quickly jump around to different courses. Here, you can quickly jump to
This
related
is
topics.
exactly like
There are
Khan
tons of
Academy.
friendly practice questions for you too. You can try it in two ways. You can first try the practice, and then watch a teacher work through the examples step by step. Or you can jump directly to an example walkthrough and learn. If you really don't get the topic, it may be because you missed an earlier class. We've got that figured out for you too. Look, why spend 30 minutes on a lecture when we can help clarify a concept in 5 minutes by walking you through real examples? StudyPug focuses on walking through the questions that you see in tests and exams. You know, the type that you never learn in class, but trip you up in the finals. We have literally thousands of example videos covering every type of questions you will probably see, organized according to your class. Then we keep you focused on success by building out a personal plan for you and track which top.
Hi, I'm Carrie Ann, and this is Crash Course Science. And today, we're going to talk about how computers store and represent your data, which means we've got to talk about math. But don't worry, every single one of you already knows exactly what you know to follow along. So last episode, we talked about how transistors can build logic gates, which can evaluate Boolean statements. And in Boolean algebra, there are only two binary values, true and false. But if we only have two values, how in the world do we represent information beyond just these two values? That's where the math comes in. So as we mentioned last episode, a single binary value can be used to represent a number. Instead of true and false, we can call these two states 1 and 0, which is actually incredibly useful. And if we want to represent larger, we just need to add more binary digits. This works exactly the same decimal numbers we're all familiar with. With decimal numbers, there are only 10 possible values of single digit 0 through 9. And to get numbers larger than 9, we just start adding more digits to the front. We could do the same with binary. For example, let's take the number 263. What does this number actually represent? Well, it means we've got two 100s, 6 tens and 3 1s. If you add those all together, we've got 203. Notice how each column has a different multiplier. In this case, it's 100, 10, and 1. Each multiplier is 10 times larger than the right. That's because each column has 10 possible digits to work with, 0 through 9, after which you have to carry one to the next. For this reason, it's called base 10 notation, also called decimal, since decimal is 10. And binary works exactly the same way. It's just base 2. That's because there are only two possible digits in binary, 1 and 0. This means that each multiplier has to be 2 times larger than the column to its right. Instead of hundreds, tens, and ones, we now have fours, twos, and ones. Take, for example, the binary number 101. This means we have 1 4, 0 2s, and 1 1. Add those all together, and we've got the number 5 in base 10. But to represent larger numbers, binary needs a lot more digits. Take this number in binary. We can convert it to decimal in the same way. We have 1 times 120.
Oh. Looks like a plus.
0 times 64, 1 times 32, 1 times 16, 0 times 8, 1 times 4, 1 times 2, and 1 times 1, which all adds up to 180, 0 as our sum and 1. Just like in our decimal example, 1 plus 1 plus the one carried equals 3, or 1 1 in binary. So we put the sum as 1 and carry 1 again, and so on. We end up with this number, binary. So we put the sum as 1. And carry one again, and so on. We end up with this number, which is the same as the number 202 in base 10. Each of these binary digits, 1 or 0, is called a bit. So in these last few examples, we were using 8-bit numbers, with their lowest value of 0 and highest value of 205, which requires all 8 bits to be set to 1. That's 200.
This is a number for colors, right? 0 to basically
56 different values, or 2 to the 8th power. You might have heard of 8-bit computers, or 8-bit graphics or audio. These were computers that did most of their operations in chunks of 8 bits. But 256 different values isn't a lot to work with. So it meant things like 8-bit games were limited to just 256 different colours for their graphics. And 8 bits is such a common size in computing, it has a special word, a byte. A byte is 8 bits. If you've got 10 bytes, it means you've really got 80 bits. You've heard of kilobytes, megabytes, gigabytes, and so on. These prefixes denote different scales of data. Just like 1 kilogram is 1,000 grams. 1 kilobyte is 1,000 bytes. Or really 8,000 bits. Mega is a million bytes, and giga is a billion bytes. Today, you might even have a hard drive that has
billions. Billion?
1 terabyte of storage. That's 8 trillion ones and zeros. But hold on, that's not always true. In binary, a kilobyte has 2 to the power of 10 bytes, or 1,024. 1,000 is also right when talking about kilobytes. We should acknowledge it isn't the only correction. You've probably also heard the term 32-bit or 64-bit computers. You're almost certainly using one right now. What this means is that they operate in chunks of 32 or 64 bits. That's a lot of bits. The largest number you can represent with 32 bits is just under 4.3 billion, which is 32 ones in binary. This is why our Instagram photos are so smooth and pretty. They are composed of millions of colours, because computers today use 32-bit color graphics. Of course, not everything is a positive number, like my bank account at college. So we need a way to represent positive and negative numbers. Most computers use the first bit for sign, 1 for negative, 0 for positive numbers, and then use the remaining 31 bits for the number itself. That gives us a range of roughly plus or minus 2 billion. While this is a pretty big range of numbers, it's not enough for many tasks. There are 7 billion people on the Earth, and the US national debt is almost $20 trillion after all.
This is why
64-bit numbers are useful. The largest value a 64-bit number can represent is around 9.2 quintillion. That's a lot of possible numbers. We'll hopefully stay above the US national debt for all. Most importantly, as we'll discuss in a later episode, computers must label location memory, known as addresses, in order to store and retrieve value. As computer memory has grown to gigabytes and terabytes, trillions of bytes, it was necessary to have 64-bit memory addresses. In addition to negative and positive numbers, computers must deal with numbers that are not whole numbers, like 12.7 and 3.14, or maybe even stardate 439.1. These are called floating point numbers because the decimal point can float around in the middle of a number. Several methods have been developed to represent floating points, the most common of which is the IEEE 754 standard. And you thought historians were the only people bad at names. In essence, this standard stores decimal values sort of like scientific notation. For example, 625.9 can be written as 0.659 times 10 to the power of 3. There are two important numbers here. The 0.6259 is called significand, and 3 is the exponent. In a 32-bit floating point number, the first bit is used for the sign of the positive or negative. The next 8 bits are used to store the exponent, and the remaining 22 bits are used to store the significand. Okay, we've talked a lot about numbers. Your name is probably composed of letters, so it's really useful for computers to also have a way to represent text. However, rather than have a special form of storage for letters, computers simply use numbers to represent letters. The most straightforward approach might be to simply number the letters of the alphabet, A being 1, B being 2, C 3, and so on. In fact, Francis Bacon, famous English writer, used 5 bits to encode all 26 letters of the English alphabet, send secret messages back in the hundreds. And 5 bits can store 32 possible values. So that's enough for 26 letters, but not enough for punctuation, digits, and upper and lowercase letters. Enter ASCII, the American Standard Code for Information Age. Invented in 1993, ASCII was a 7-bit code, enough to store 120 different values. With this expanded range, it can encode capital letters, lowercase letters, digits 0 through 9, symbols like the @ sign and punctuation mark. For example, a lowercase a is represented by the number 7, while a capital A is 65, a colon is 58, and a closed parenthesis is 41. ASCII even had a selection of special command codes, such as a new line code, tell the computer where to wrap a next row. In older computers, the line of text would literally continue off the edge of the screen if you didn't include a new line character. Because ASCII was such an early standard, it became widely used and critically allowed different computers built by different companies to exchange data. This ability to universally exchange information is called interoperability. However, it did have a major limitation. It was really only designed for English. Fortunately, there are 8 bits and not 7, and it soon became popular to use codes 120 through 255, previously unused, national characters. In the US, those extra numbers were largely used to encode symbols, like mathematical notation, graphical elements, and common accentuated characters. On the other hand, while the Latin characters used universally, Russian computers the extra codes Cyrillic characters, and Greek computers Greek letters and so on. And national characters worked pretty well for most countries. The problem was, if you opened an email written in Latvian or Turkish, the result was completely incomprehensible, and things totally broke with the rise of Asia. As languages like Chinese and Japanese have thousands of characters, there was no way to encode all those characters in 8 bits. In response, each country invented multi-byte encoding schemes, all of which were mutually incompatible. The Japanese were so familiar with this encoding problem, they even had a special name for it, Moji Bouquet, which means scrambled text. And so it was born, Unicode, one format to rule them all. Devised in 1992 to finally do away with all of the different international schemes, it replaced them with one universal encoding. The most common version of Unicode uses 16 bits with space for over 1 million codes, enough for every single character from every language ever used. More than 120,000 of them, in over 100 types of script, plus space for mathematical symbols and even graphical types like emoji. And in the same way that ASCII defines the code for encoding letters as binary numbers, other file formats like MP3s or GIFs use binary numbers to sounds or colours of pixel in our photos, movies and music. Most importantly, under the hood, it all comes down to long sequence bits. Text messages, this YouTube video, every web page on the internet, and even your computer's operating system are nothing but long sequences of ones and zeros. So next week, we'll start talking about how your computer starts manipulating binary sequences. For our first true taste of computation. Thanks for watching. See you next week. Crash Course
Computer Science is produced in association with PBS Digital Studio.
At their channel, you can check out a playlist.
Like all the people that work in building computer science, like like way back, they are completely genius, and now too, like completely genius.
Of shows like Physics Girl,
Deep Look, PBS Space.
This
This episode was
Genius. Okay. I'm done for today. 2 hours. Not for today, but I'm done for now. Let's go back in like 2 hours. Yeah. Alright. See you guys later. See you guys later.